Hello everyone and welcome back to the Math Explorer. Today we are diving into an exciting and fundamental topic in abstract algebra, fixed fields and size of automorphism groups of splitting fields. If you are passionate about Galois theory in mathematics or just looking to deepen your understanding in the said domain, you are in the right place. But before we get started, make sure to hit the subscribe button and click the bell icon so you don't miss any of our future lectures. If you find this video helpful, give it thumbs up and share it with your fellow math enthusiasts. Alright, let's jump right in. First, let's talk about what is a fixed field and how can we find it in case of subgroups of automorphism groups. Dear students, suppose we have a field K as we talked in the previous lectures as well. So suppose K is a given field to us and we are having automorphisms of K. So suppose I have the set of all automorphisms of K. So out of K refers to automorphisms of K, right? And suppose H is a subgroup of out of K. Now we are interested in the elements of K which are fixed by the elements of H. Okay, so let me just tell you this. Suppose K is a field and you are just calculating set of all automorphisms of K and we have a subgroup H of automorphism of K. I'm interested in the elements of K, say, or we can just have it diagrammatically. Suppose this is my K and suppose H is a subgroup of out of K. So I'm interested in the elements of K, say these elements which are fixed by the elements of H. Okay, so let's talk about it. First of all, we'll show that all these elements forms a subfield of K. So my first point in the today's lecture is this: the collection of elements in K fixed by all the elements of H is a subfield of K. Don't forget that H is a subgroup of automorphism group of K. Now let's try to prove this. So to begin, we'll first of all write down the set which we are interested in. So I will call that set as F. So let F equal to, say, alpha belongs to K such that sigma of alpha equal to alpha for all sigma belongs to H. That means these are the elements of K which are fixed by all the elements of H. Now our claim is that this F is a subfield of K. We know the basic idea. How can we show a set to be a subfield? To show that, we require to prove that addition, subtraction, multiplication and division, in case where denominator is not 0, all these elements should belong to F. We are taking some elements of F. So let me start with two elements of F. So let me take A and B belongs to F. Okay, so this means A and B are fixed by all the elements of H, right? So this implies sigma of A equal to A and sigma of B equal to B for all sigma belongs to H as per the definition of F, right? As we have defined F here. Now I want to prove that. Let me write it as subclaim. So I want to show that A plus B, then A minus B, then A into B, then A upon B, provided B is non-zero, all these elements belong to F again. And that's quite easy to establish. So let sigma belongs to H be n element. Let us consider any automorphism of K which is in H be n element. then sigma of a plus b. Since sigma is automorphism of k, it is an element of H, but H is a subgroup of auto of k, so sigma is automorphism of k, right? So that's why sigma is itself a homomorphism. So that's why sigma of a plus b is equal to sigma of a plus sigma of b. But we already know that sigma of a equals to a, sigma of b equals to b. So sigma of a plus b equals to a plus b. We can also establish the fact that sigma of a minus b is equal to sigma of a minus sigma of b, because sigma is homomorphism, so that is again a plus b, a minus b, right? Then sigma of a into b is equal to sigma of a into sigma of b, as sigma is homomorphism, so that is equal to a into b, because sigma of a equal to a and sigma of b equal to b. And finally, sigma of a upon b, that is sigma of ab inverse, that is simply sigma of a into sigma of b inverse, but sigma of b inverse is sigma of b whole inverse, so this is sigma of a into sigma of b whole inverse, and that is a into b inverse again, that is a upon b. So this clearly implies that addition, subtraction, multiplication and division, okay, or it could have been sufficient if we have proved it for inverse only, that is sigma of a inverse is equal to a inverse itself. So anyway, we have proved it for a upon b, so that doesn't matter. So all these elements are in F, so that's why F is a subfield of K. So this shows that F is a subfield of K, right? So now we are interested in the fixed field of this H, a subgroup of automorphisms of K which we considered in the beginning. So I'm interested in the fixed field of that H. Okay, so let me define that now. So definition, so let H be a subgroup of out of K, as we have already assumed, right? Then subfield of K, because we have proved that set of all elements in K which are fixed by all the elements of H forms a subfield of K. So then subfield of K fixed by all the elements of H is called as fixed field of H. Now, after the definition of fixed field, we will prove some interesting but yet important properties here. So let me prove some properties. The first one, so if F1 is contained in F2 and F2 is contained in K, are two subfields of K then group of automorphisms of K over F2 is a subgroup of group of automorphisms of K over F1. It is very interesting and very easy fact to establish. So we will quickly go for a proof. So let me first of all show that this particular set of all automorphisms of K over F2 is a subset of set of all automorphisms of K over F1. So let me assume some element sigma from set of all automorphisms of K over F2. So this clearly means that sigma is automorphism of K and it fixes F2, right? So this implies sigma of A equal to A for all A belongs to F2, because sigma is automorphism of K over F2, that means it fixes F2, okay, and sigma belongs to out of K, right? So what this implies, we have already given that F2 is a superset of F1, and if sigma is fixing a superset, then definitely it fixes a subset, right? So that's why I can write here that this implies sigma of A equal to A for all A belongs to F1 as well, and the reason is quite clear, that because F1 is contained in F2, right? So now sigma is automorphism of K which fixes F1, so this clearly implies sigma belongs to automorphism of K over F1, right? So that's why out of K over F2 is a subset of out of K over F1, so thus out of K over F2 is a subset of out of K over F1. But the interesting point is that out of K over F2 is a subset of out of K over F1, but out of K over F2 is a subgroup of out of K, because it is again a subset of a set of all automorphisms of K, right? So the fact that I want to clarify here is this. See, this is your set of all automorphisms of K, right? And out of all these automorphisms, you are selecting automorphisms of K which fixes F2. So suppose these are automorphisms of K, those which fix F2. And we have already established that this set of automorphisms of K over F2 is contained in automorphisms of K over F1, right? But automorphisms of K over F2 is a subset of out of K, it's already a subgroup of out of K, right? So this particular out of K over F2 is a subgroup of out of K, right? And it is contained in out of K over F1, so clearly it is subgroup of out of K over F1. So because it is contained in this and it is subgroup of out of K, so it is subgroup of out of K over F1 also. Okay, so we can write that since out of K over F2 is a subgroup of out of K, subgroup of out of K, comma, clearly out of K over F2 is a subgroup of out of K over F1. That's it. So this is the first fact that we have established now. Now let's move to the second interesting property. So if H1 is a subgroup of H2 is subgroup of automorphism of K, so we are considering two different subgroups of automorphisms of K, and as we have established in the previous discussion that fixed fields of subgroups of automorphisms of K, so with let me say with associated fixed fields, so let me say that fixed fields, assume that fixed field of H1 is F1 and fixed field of H2 is F2, means F1 is set of all elements in K which are fixed by elements of H1, and F2 is set of all elements in K which are fixed by H2 respectively. Then F2 is contained in F1, right? This is again very easy to prove. Okay, so let's establish this fact. So let me take, let X belongs to F2. So as per the definition, since X belongs to F2, it is fixed by all the elements of H2. So this implies sigma of X equal to X for all sigma belongs to H2, right? But H1 is subset of subgroup of H2, right? So if all the elements of H2 are fixing X, then definitely all the elements of H1 do fix X, because that is a subset of H2 actually. So this implies sigma of X is equal to X for all sigma belongs to H1 as well. Reason is simple, as H1 is subgroup of H2. If superset fixes X, then definitely subset fixes X, right? So this is implies sigma of X equal to X for all sigma belongs to H1, and that's why X belongs to F1. So we begin with X belongs to F2, we ended with X belongs to F1. So clearly F2 is contained in F1, and that concludes the simple proof. Now we will find fixed field of some fields here. So let me take one example. So example is this: find the fixed field. Find the fixed field of out of K where K equals to Q root 2, right? So as we have discussed in the previous lecture as well, which you can find in my videos on YouTube. So the automorphisms of this particular field K, because root 2 satisfies polynomial x square minus 2 with distinct roots root 2 and minus root 2. So root 2 can map to root 2 or root 2 can map to minus root 2. So we have out of K equal to two automorphisms, sigma 1, sigma 2, where sigma 1 is defined as identity. So sigma 1 of a plus b root 2 equal to a plus b root 2, and sigma 2 of a plus b root 2, where a plus b root 2 is element of q root 2, is equal to a minus b root 2, because root 2 also maps to minus root 2. Now we want to find fixed field of this whole automorphism group, right? So we want to fix field of whole out of K. Okay, so we want to find all the elements of q root 2 which are fixed by both sigma 1 and sigma 2. But keep in mind that sigma 1 is identity map, right? So it fixes all the elements of q root 2. Okay, so we can easily say that this is identity map, so it fixes all the elements of q root 2. Now we only want to find out those elements which are fixed by sigma 2. So let's try to identify those elements. So we want now sigma 2 of a plus b root 2 should be equal to a plus b root 2, means all the elements of K which are fixed by sigma 2. But as per the definition, sigma 2 of a plus b root 2 is a minus b root 2. So that should be equal to a plus b root 2. If you try to solve this, you will easily come to the conclusion that 2 times b root 2 equals to 0, right? But this simply means b equal to 0. So that means sigma 2 only fixes purely rational numbers, right? And sigma 1 fixes all the elements of q root 2. So the element fixed by both is nothing but set of rational numbers. So fixed field of out of K is set of all rational numbers. So that's how we can find the fixed field. Now we are moving to a very interesting and important fact, that is size of automorphism group of splitting field. Okay, so the next point of discussion is size of automorphism group of splitting field. Okay, so let's start with this. So theorem is like this: let E, capital E, be the splitting field of f of x belongs to fx over f, then size of automorphism group of splitting field E over base field F, that size is always less equal degree of extension of E over F, degree of extension of E over F, right? and when they are equal, so equality holds if f of x is separable over f. Now we are here with two different terms actually, so we we are unaware of those terms. So the first term is this splitting field, and the second term is separable polynomial. So let me quickly tell you what is the splitting field and what is separable polynomial, so we can move to the proof, right? So let me just tell you this by example. Suppose q is my base field, and I am assuming a polynomial, say x cube minus 2 over q, and the question is I want to find out splitting field of x cube minus 2. So to do that, I will first of all find out the roots of x cube minus 2. So I will take x cube minus 2 equal to 0. That will imply x cube equal to 2, and using roots of unity argument, we can easily tell that x equals to 2 raised to 1 upon 3, or 2 raised to 1 upon 3 omega, or 2 raised to 1 upon 3 omega square, where omega is a cube root of unity, right? Omega is a cube root of unity, that is omega cube equal to 1. Now I want to find out splitting field. That means I want to find out field, smallest field over q, which contains all these roots. You can easily see that roots are 2 raised to 1 upon 3, 2 raised to 1 upon 3 omega, and 2 raised to 1 upon 3 omega square. So if you want to encompass all these roots over q, then you need to attach these two elements. Firstly, you need to attach 2 raised to 1 upon 3 to q, and you need to attach omega separately to q. So the splitting field of this particular polynomial over q will be q 2 raised to 1 upon 3 comma omega. That means if you attach these two elements to q, then definitely you can find all the roots of this polynomial over in this field. So this is your splitting field. So in base, splitting field is nothing but a field which contains all the roots of polynomial, smallest field over given field that contains all the roots of given polynomial, right? So that is a splitting field. And separable polynomials means a polynomial with distinct roots. Okay, so let me just write it here. So separable polynomial is nothing but a polynomial with distinct roots over given field. Polynomial with distinct roots, or we can say that all the roots are simple. That means none of the root is repeated. So polynomial with distinct roots. Okay, so that is idea of separable polynomial. So let's now start the proof of our theorem that we want to find out size of automorphism group. Okay, so let me first of all assume the things given to us. Okay, so let f be a field as given to us. So let f be a field. Okay, so suppose this is your f, right? And f of x belongs to fx be a given polynomial, and f of x over fx be a given polynomial. So you can easily see that so f of x is defined over f. Okay, let E be the splitting field of f of x. So let E be the splitting field of f of x. Splitting field of f of x means the extension of f which contains all the roots of f of x, right? So E is splitting field of f of x. Okay, now we want to find out the size of automorphism of proof of E over f, automorphisms of E over f. So the base point is that if we are provided with any automorphism, say let me just explain that idea. Suppose you are provided with automorphism from f to f dash, say sigma, then you can extend this automorphism to e to e dash, where e is a splitting field of f of x and e dash is a splitting field of sigma of f of x. Okay, So in this way we can extend these homomorphisms. I will further explain this idea in the proof. Okay, so what now we are going to do, we are going to use induction hypothesis on the degree of extension of E over F. So we will prove this. We will prove this by induction hypothesis. Okay, or you may just say induction on degree of extension of E over F. Now the idea which I was trying to explain you is this. Suppose f is a field given to you and f of x is a given polynomial, right? Now suppose you have calculated splitting field of this f of x and that splitting field is E. Now what happens, there is another field f dash, okay, and suppose sigma, or we may just instead of sigma I would like to prefer it with some other, say psi. So suppose psi is a automorphism from f to f dash. So definitely this polynomial can be shifted to f dash. So it is psi of f of x, right? Or we can call this as f dash of x. Okay. Now splitting field of that f dash of x is E dash. Okay. The point is that you can extend this automorphism between fields to the automorphism between splitting fields. So you can extend this to sigma from E to E dash. Now we only need to find how many such extensions are possible, how many ways we can extend this psi to sigma. That is going to be the number of automorphisms of E over F. The point is that psi is a basic automorphism given to you, okay, and if you have extended psi to sigma, it is quite obvious that sigma is natural, means it depends on psi on F, right? So that's why you only need to find out the extensions of psi to sigma, and that will give you your answer. Now we will do it by degree of extension of E over F. So I will just abbreviate all these concepts. So if degree of extension of E over F equal to 1, this clearly implies that E equals to F, and if E equals to F, then definitely E dash equals to F dash, because E and F are same, so E dash F dash will be same. So this implies E dash equals to F dash, right? And in this case extension is only one, that is identity, nothing else. Okay, so in this case cardinality of automorphisms of E over F will be equal to 1. Only one extension is possible because there is E and F are same, E dash F dash are same, so there is only one extension, and that is equal to degree of extension of E over F. Now assume that degree of extension of E over F, suppose degree of extension of E over F is greater than 1. Now since degree of extension is greater than 1, okay, it means splitting field is not F. So splitting field is larger than F. That means there is some root which is not in F, and that root is outside F. Okay, if all the roots of given polynomial are in F, then splitting field could have been F. But since splitting field is not F, because degree of extension is more than 1, it means there are some roots which are outside F. And if there are such a roots, there must be a quadratic factor, irreducible quadratic factor, because all the factors cannot be linear factors, right? So there must be a quadratic factor, irreducible quadratic factor, say p of x. Okay, so suppose let p of x be irreducible quadratic factor, or instead of saying quadratic you can just say that of degree greater than 1. So p of x be irreducible factor of f of x with the degree of p of x greater than 1. So let me just show it by a diagram. So now the situation is like this. We have f, we have f dash, and there is a automorphism between f and f dash. This is your E splitting field of f of x, this is your E dash splitting field of f dash of x. Okay, call this as sigma, and now we have irreducible factor of f of x. So f of x is a polynomial defined over f, and we have irreducible factor p of x, so it lies in between. Okay, so let me assume some root of that p of x. So if p of x is irreducible factor of f of x, then p dash of x means image of p of x is irreducible factor of f dash of x. Okay, that's quite obvious. Means if p of x is here, irreducible factor of f of x, then p dash of x is here, which is irreducible factor of f dash of x. F dash of x is image of f of x, right? So that's quite simple to understand. Now let alpha be the root of p of x. So let alpha be the root of p of x. Now what happens, because of this alpha, we can just attach this alpha to f, because it is root of p of x. So we can attach this alpha to f, so we will have f alpha, right? And if alpha is root of p of x, then we can just extend this psi to some automorphism, say sigma. Instead of sigma I can say tau, because it's a repeated symbol. So psi can be extended to tau from f alpha, and this tau is completely determined by tau of alpha, because what happens, psi has found out all the images of elements in f. Alpha is newly attached element to f. Okay, so to define tau, we need to find out image of alpha under tau. Okay, so we are only interested in what is tau of alpha, but alpha is a root of p of x, so definitely tau of alpha is a root of p dash of x. So that is some beta, you may say some beta. So here we can take f beta, okay, and where alpha maps to beta, and beta is a root of p dash of x. Okay, so in this case, in this way we can extend the automorphism psi from f to f dash. Now what happens, there is a two-way extension. Psi will first of all will be extended to tau, and tau will be extended to sigma. Okay, now let me tell you, we will just focus on this diagram to conclude the proof. Number of extensions of this psi to sigma can be counted, that in how many ways we can extend psi to tau, and in how many ways can we extend tau to sigma. Okay, now what happens, see what is degree of extension of e over f alpha. So we can easily say that degree of extension of e over f alpha is less than degree of extension of e over f, right? And by induction hypothesis, because we are taking induction on degree of extension of e over f, so by induction hypothesis, our assumption is true for all the fields E whose degree of extension over f is less than degree of extension of E over f. So since degree of extension of E over f alpha is less than degree of extension of E over f, by induction hypothesis, number of automorphisms, that is number of extensions of tau to sigma, is less than E over f. Okay, so less than degree of extension of E over f. That's quite easy to understand. And further, now we need to identify, so let me just tell you. So induction hypothesis is true for degree of extension of E over f alpha, because it is less than E over f. So the number of extensions of tau to sigma is less equal degree of extension of E over f alpha by induction hypothesis, because the result is true for all the fields with degree of extension less than degree of extension of E over f. So it is less equal E over f alpha. That's one point. Now the point is that how many extensions are there for psi to tau. Okay, in how many ways you can extend psi to tau. So extension completely depends on alpha. So it depends completely on how many roots are there for p of x. Okay, so the number of root, if you are taking alpha as a root, you can find extension. Similarly, if beta is a root of p dash of x, you can find extension. So extension completely depends on roots alpha and beta. So it's only interesting point that how many roots are there for p of x and p dash of x. But understand that degree of p of x and degree of p dash of x equals to degree of extension here. Okay, because we are attaching the root of p of x and p dash of x to this particular f to extend these fields. So basically degree of p of x and degree of p dash of x is equal to degree of extension of f alpha over f. Okay, So number of extensions psi to tau will be at most degree of extension of f alpha over f, at most, because we are not sure about the roots. Okay, the roots may be repeated. We cannot exactly say that number of roots of p of x is exactly equal to degree of extension, because root may be repeated. So we are not quite sure about it. So the number of extensions of psi to tau, okay, is less equal degree of extension of f alpha over f, because the number of roots can be less than degree of extension. I'm not saying about cardinality of roots. I'm saying that if some root is repeated, we will only find only one extension. Even if the root is repeated twice, we will find only one extension. The number of extensions is less than degree of extension of f alpha over f. So finally, what is the total number of extensions of psi to sigma? So you can easily find. So the total number of extensions of psi to sigma is less equal psi to tau and tau to sigma. So less equal e over f alpha into f alpha over f, and that is equal to degree of extension of e over f. And number of extensions of psi to sigma is nothing but automorphisms of e over f, right? Which fixes f. So that means cardinality of automorphisms of e over f is less equal degree of extension of e over f. That's the proof. Now when it will be equal? So as I told you, it will be equal only when all the roots of p of x are distinct. Means here we are talking about p of x. If all the roots of p of x are distinct, number of extensions will be exactly equal to degree of extension. And in this case, when you are talking about e, then we need to focus on f of x, because e is a splitting field of f of x. So if all the roots of f of x are distinct, then only number of extensions will be exactly equal to degree of extension of e over f alpha. So in short, if all the roots of f of x are distinct, that means if f of x is separable polynomial, then only size of automorphism group is exactly equal to degree of